Thank you for joining me today. As you can see on the screen here, my name is Richard Barry and I am a Senior Principal Engineer with AWS IoT, that is Amazon Web Services Internet of Things. And very specifically, I work on the things, that is the devices that connect to IoT services. However, I'm best known as the original author of FreeRTOS, which is an MIT licensed, so open source, real-time operating system. FreeRTOS has been around for very nearly 20 years. It's been ported to more than 40 different architectures and 20 different compilers. Those architectures range from small 8-bit devices all the way up to very big 64-bit devices. Really, the niche, though, is 32-bit microcontrollers. We have a code size of anywhere between kind of 9 and 18 kilobytes of program space. So it fits very nicely into that 32-bit microcontroller space. And if you're wondering about the connection between a small operating system and a cloud provider, well, there are many millions of devices that run FreeRTOS which are connecting to cloud services, including AWS IoT. So we're working together to make sure those devices can connect as quickly and as securely as possible. The more we can provide the undifferentiating functionality, the more our users can spend more of their time developing the value-adding differentiating functionality. So this diagram is showing the number of downloads of FreeRTOS over the last 18 years. It's downloaded about once every 170 seconds at the moment. If you look at the end of this graph, you will see that the line changes color. That is where we move to GitHub. So FreeRTOS predates Git, yet alone GitHub. And what we've done recently is to refactor a lot of the libraries to make sure they don't have any dependencies on each other. Actually, the TCP/IP stack has a dependency on the kernel, but everything else doesn't. So we've placed them all in their own Git repositories. That enables users to just submodule in the libraries they need, and there's no dependency even on multi-threading. In some cases, there's no dependency on the kernel, there's no dependency on the TCP/IP stack even. I'll talk about that a little bit more later with a bit of a diagram to show you what I mean. This is just showing the growing number of unique visitors on the freertos.org site as well. So what are we talking about today? Well, I'm going to expand on what we spoke about last year. At last year's event, I kind of introduced FreeRTOS IoT reference integrations. These are integrations of libraries that together create or provide, all the functionality you need to connect securely to a cloud service. At the end of that talk, we looked at how you can port those devices to any microcontroller which is running the TFM code. So there's a few acronyms here. Let's see what these things mean. TFM is Trusted Firmware-M. It is a reference integration provided by ARM for microcontrollers, a reference implementation of the PSA APIs. So PSA is ARM's platform security architecture. Now, FreeRTOS likes to ensure that it uses kind of open standards for everything to make sure we're not locking users into any particular ecosystem. So within the reference integrations, we use the open PKCS11, which is the public key crypto standard 11 API for security operations. This provides a kind of session-based access to things like private keys, certificates, that kind of thing, to make sure that they're not exposed to even the code which is running on the device. If you have hardware support with things like secure elements, secure enclaves, that kind of thing. Now that requires porting to that secure enclave or whatever's available in your hardware. So there is a mapping of, well, a porting, if you like, of that PKCS11 to TFM to enable any device which is running ARM's TFM code not to have to port it, they just use it. So today we're extending that to make use of the TFM's over-the-air updates or OTA, another acronym, API. So we'll look a little bit about what OTA is, some of the use cases for OTA, in particular how it's used with security, and then look a little bit at how that mapping works and how you can use the OTA service with the TFM Implementation of PSA. Now, FreeRTOS, using this mapping, FreeRTOS is certified to be compliant with the PSA API. Now, you can use OTA over-the-air updates for lots of different things. This is the ability to send over the air, given the name, hence the name, a file to a remote device. This is very important, of course, for many reasons. You've got millions of devices. They're not necessarily physically accessible to you. You may want to do something like update the functionality. You may want to unlock functionality. You may want to update credentials that are on device that enable it to rotate credentials if that's part of your security policy. For this talk, though, we're going to focus predominantly on using OTA as a key element of security. I've listed out a few things that we are or that we're going to have to take into consideration. Maybe you have a security policy or security practices that your enterprise implements, and these are the things that you are going to consider as part of that, presumably. Credentialing and secure onboarding. This is getting the IoT device to connect in the first place to the correct cloud, to be able to authenticate when it does that, and configured in a way that protects sensitive data. That's an interesting topic in itself. Different use cases require different ways of getting those credentials onto the device in the first place. I did a talk about that at AWS's reInvent conference last year, if you want to go and look at that. And then, from there, we are building, the monitoring, best practice, monitoring your devices, so you know how your devices are behaving. You can check for anomalies, lots of different things you can monitor for. And then, as I say, if you have a security policy, you can use the information that you gather from that monitoring to audit your devices against your policies. Now, if you find any deviations from your policy, you want to remediate the deviation, bring your device back into compliance, that may require a new executable image or new credentials to be sent to your device. And this is where OTA and patching comes into this security story. Okay, here now I am looking at 3 devices. I was trying to look at devices in different kind of industry verticals because FreeRTOS and IoT is used across a whole raft of different industries. I think all industries in reality. So let's think about disconnected use cases first, so then we can kind of bring in the value of IoT as well. The first thing is a door lock, top left here. This might be a numeric keypad, so there's a little bit of programming in there. And if I've got physical access to that keypad, I can change the code to get access to the lock, open the door. The next, we've got an actuator. Maybe this is a motor in a factory. IoT brings huge value to industrial use cases. And maybe this has got a little bit of local connectivity, RS485, so it can receive a torque or a velocity command and maybe reply with its position, very, very basic. And then at the bottom we have sensors. If this was just a temperature sensor, it could be building management. If it's a vibration sensor, maybe it's monitoring the motor, which is in the factory, so it can detect worn bearings or something like that. Now, if I can bring in the program space, the memory map here, you can see that the primary functionality is not going to take up much program space. And that basic connectivity is also not going to bring much program space. A simple 485 protocol, for example, we have a little bit of communications protocol to implement, a little bit of program space. But what if we want to get the value of internet connecting these devices? So what can we do here? Let's say we internet connect our keypad door lock. Now, if I have a vacation rental property and in between people who are renting that property, I don't want to have to go out there and physically reprogram it. Now I can do that over the internet. Maybe in our industrial scenario, we have the combination of the motor and the vibration sensor here. We can add value by having diagnostics. We can predict preventative maintenance. We can predict when that device is going to go wrong by the temperature or the vibration. Maybe there's some machine learning. Our local device doesn't have the capability, it's too small to do the machine learning, so we can offload that to the cloud. It can learn how that motor behaves, and then we can predict when it goes wrong and bring huge value by not having to maintain it regularly, but just replace it, replace bearings or something, actually before it goes wrong, before we get that downtime. So here we are adding a little bit of, intelligence into our devices, so I can increase the program space to implement that intelligence. But now what happens from a security perspective? You have all those, security things that we have to consider. And now that our device is connected to a public network, right? We're going to have to consider these things, because maybe there is data which is private. We need to maintain customer trust by ensuring privacy. Maybe the data going backwards and forwards is valuable data, and we want to maintain our position in the market, or our own kind of confidentiality. We need to protect that data. So these security considerations are coming in to the device side. And here we can see the kind of impact of that on our program space, right? There's a lot more code here, right? So we can go through, we can see why this is, right, and go through and see where OTA fits into this on our device. So starting at the bottom again, we've got a little bit more program space, but our communication stack now has to go across the internet, so it has to be more sophisticated and hence is larger. If we want to do things like authenticate to a cloud service, make sure we're connecting to the correct place, and the cloud needs to authenticate us to make sure that we are, we have the authority to connect, and we want to, encrypt data in flight, and we want to check signatures of images, that kind of thing. Then we're going to need secure storage for those keys, but more importantly, we're going to need the security protocols. TLS is very common here. So TLS is the same protocol you use every time you connect to an HTTPS server to make sure you're connecting to the correct server and the encrypted data, right? So that's, a fair whack of code. And then, for the monitoring, we have the logging and, sending data to the cloud that enables it to audit us. I mentioned the secure storage already. The over-the-air update then, so we can receive new security credentials, and we can receive patches, as I said, if we're remediating something which is out of compliance. And then, of course, with that OTA, we need the bootloader as well, as will become evident as we talk through these things. So that's a lot of code, isn't it? And here I'm highlighting the part of that code which is differentiating. This is the bit we want to concentrate on to add value to our product, of course. Now I'm going to highlight all the bits which are undifferentiating, and we can see this is the majority of the code. And this is where the IoT reference integrations help, because we are providing that undifferentiating functionality to enable you really to focus on the primary functionality, the primary differentiation. Now, of course, providing undifferentiating functionality is one of the primary value propositions in the cloud as well. Here I am kind of demonstrating a cloud service. All the kind of icons you see here are running in the cloud now, not on the device. The devices are off the left-hand side of the image. They are going to send their data through that little cloud icon with the door. That's representing the gateway into the cloud. But there, the same considerations apply. If I relate this specifically to AWS IoT, and we think about, the credentialing, we have IoT Core, which is you connect to using TLS. That's going to make sure that you're authenticated. And then once you are authenticated, from that point on, it knows what you are authorized to do inside the cloud. And again, we'll talk about that a bit later. Monitoring, AWS IoT specific again, we have things like CloudWatch. We can log lots of things in CloudWatch. That then enables us to do the auditing, of course, because we've got that data. But there are also services, in addition to CloudWatch, specifically to auditing and monitoring devices, things like Device Defender. And then there's many different remediation paths. If we're talking about remediating a remote device, then we have the AWS IoT Job Service. That is part of what the OTA service is built on top of. But let's get back to our device and look more detail at OTA. What does OTA involve? Well, broadly speaking, there are three components, three actors, if you like. The first is the humans, the operators. Then we have the OTA agent, and then we have the secure boot system. If we look at the operators, what are they going to do? Well, I'm lumping the developer here as an operator, or as a human really. So they're going to, if we're doing a firmware over-the-air update, they're going to build a new image. That new image is then going to be uploaded to the cloud. It might be signed and then uploaded, but in this case, we're going to upload it to the cloud and then sign it in the cloud. Signing it allows the device to make sure it's coming from the right place, it's not being tampered with, etc. And then we're going to schedule an OTA job, and then we are going to actually wait for that OTA job to complete, or not, as the case may be. So here I'm adding humans into the loop, right? So there's security risk here, of course. We've only really looked at the device side, how we're mitigating the device side, and the same as this credentialing is in the cloud as well. For humans to authenticate, and once they've authenticated, for the cloud side to know what they're allowed to do. In the middle here, I'm showing, just highlighting the IAM, which is the Identity and Access Management Service. This is where you credential users, and you get very fine-grained control. For example, on the right-hand side, there's a screenshot of the console where you are going to actually initiate an OTA. So you can say which operators are allowed to sign an image, which operators are allowed to start an OTA operation, all in the cloud side. Security then is managed device and cloud. Let's come back to the device side. This is the operators. Then we have the OTA agent. This is going to download the image. It's going to write it to Flash. Now notice when it's writing to Flash, at this point, it is doing something which is device specific. And this is where the TFM comes in. And some of the things we're looking at now during this talk. So it's going to write it to Flash and verify the signature. If the signature is okay, it's going to tell the application that it can do a reboot. And after it's done the reboot, this last step here, the yellow step here, is the boot system is going to verify the image again. In fact, it does that every time it boots. It's going to use the keys to make sure the signature is correct. It's then going to tell the image, tell the application that there's a new image, and that allows the application to test the image the first time. Once it's tested, it's either going to reject it and tell the cloud it's rejected, or it's going to commit it. From that point on, it's going to use it every time it boots, and then it's going to tell the cloud that it's passed the OTA. And it also does things like, it's going to check that the version number is incremented, not decremented. It's open source code, right? So you can change this behavior if you like. But that's the normal practice to make sure that somebody isn't rolling back to an image which has a known vulnerability in it. Now, I mentioned there that this has a little bit of a porting requirement because, some platforms, they have dual bank Flash, so you can write to, can execute from one bank and write to the other bank and then just switch them when you want to execute the new image. Some devices don't have enough Flash on board, so they're going to use external Flash, and then you've got any combination in between. So this is something, we don't know about your hardware, hence we provide this platform abstraction layer, another acronym for you, or PAL. You can see some of the functions here. If we look at the 4th API down here, OTA PAL write block, you can see this is what I was talking about. This is the bit that actually writes the, a piece of the received image, the new image, to flash memory. So normally you're going to have to port this to your hardware. But what if your hardware is already running TFM? Now, last time we were looking at the mapping the crypto APIs to TFM. You can also do the same with this OTA PAL. So this image here is representing a system with a secure and a non-secure processing environment. This could be an ARM v8M chip, for example, or it could be a dual core system where you have a completely separate chip, which is implementing your secure execution environment. On the diagram, we have the non-secure execution environment on the left, secure execution environment on the right. And in the middle, so the secure execution environment, okay, that's running the TFM code. The application code, including the kernel, is running on the left, the non-secure environment. That kind of interface between the two, which is in burgundy there, that is that's where the PSA, the Platform Security Architecture APIs are. That's our interface from non-secure to secure. And you can see here that we have on the left-hand side our OTA agent. That is calling into the PAL. So I'm just using writing to Flash as an example, but we can see there's all the other mappings in a minute. So here we are going to receive a chunk of code, and the implementation of that PAL layer calls the PSA APIs. So as long as you got the compliant code on the secure side, then you don't have to port that. This is looking at that mapping, and this is in GitHub, so I'll give you the URL as well so you can go and have a look. Porting, here you can see there's not a one-to-one mapping between these two things. We have, if we look at that right block again, you can see it's just calls the PSA API, but the close file above there is calling two PSA API functions, and that's what this mapping, this port layer provides for you. And we can look at the code here. You can see that this is just a reset device. So you've received a new image, the signature is correct, so you've authenticated that it's not been tampered with and it comes from the correct place. And then that mapping is just going to do that one-to-one for you. Right block is a little bit more, there's a little bit more to it, but it's only really error checking. It's not that much, not that much more complex really than just that single function for function mapping that was in the previous slide there. And there's a lot of code there, and the way it's organized when we have this OTA agent, that hides that complexity from the application writer, not the porter. The OTA agent is a separate thread, right? So you start it up when the application boots and it runs in the background. It registers with the cloud service. The cloud service notifies it when there's a new image. It downloads in the background, tells the application when the image is there and authenticated. Of course, if we were to look at the integrator's view, then we see all these other libraries. Now, these libraries are well, this is just one use case, right? We're using MQTT. This is the protocol that we use to communicate with the OTA agent, control plane of the OTA agent. If you have HTTP in your application, you can use that to do the actual download. If you don't, you can use MQTT to download an image as well. This one is showing that being done over Wi-Fi. Coming back to GitHub, I was saying before, how we have done work to make sure that all these libraries are modular now. The top left black box here is representing individual Git repositories which are in the FreeRTOS organization within GitHub. And here you will find the individual libraries which are not AWS IoT specific. These are just generic libraries like HTTP, MQTT. The kernel itself is in its own Git repo now. And what did I say, MQTT? I'm not sure. On the right-hand side, this is the black box at the top. This is representing the individual Git repositories which are in the AWS organization in GitHub. And here you can see the clients which are accessing the AWS IoT value add services. And they use the generic libraries. So the green boxes then represent collections of libraries, packages of libraries. These submodule in the individual libraries, so you can demonstrate how to submodule them into your application. If you're using the long-term support version, the LTS, yet another acronym for you there, and you might want to submodule in the LTS version, and when it's patched, you just change the submodule pointer to bring the patched version into your application. So they demonstrate how to do that. These packages demonstrate how to do that. They also include lots of examples for you as well. And this opens up the use cases that we can see at the bottom there. Okay, so I said this was the GitHub, the GitHub URL. So you can go and look at the very, very simple mapping between our PAL and the PSA API. You can also try a complete reference integration. If you go to this URL, then you will find information on how you can obtain a complete reference that is running on an STM32U5 discovery kit. That's an ARMv8-M device. I would also encourage you to come to the FreeRTOS.org website, to the forums. The forums are very active. You can use the forums as a mailing list as well if that's how you prefer it, depending on how you set it up. There you'll find lots of community members and developers of FreeRTOS who are answering questions, solving problems for people. And there's the URLs of the GitHub organizations as well. And that's it. So just leaves me to say thank you once again, and hope to see you as part of our community soon.